Hey everybody. Okay, looks like we've kind of started chapter 21. We've done all the conceptual PowerPoint type stuff already, and then we started in the preparation of amines section, which we already kind of showed you one reaction here. And like if our goal is to take an alkyl halide and convert it to an amine, it seems like a pretty easy thing, as we mentioned. And one of the ways you could do that is just use ammonia, NH3, to kick off the Br and then lose the proton, and then you have a primary amine like this. But the problem, as we learned, was that, as I kind of stepped through, is that yes, that happens. NH3 attacks, kicks it off, and then you lose a proton. But then you get a primary amine, which is great, except the primary amine keeps going and kicks off another Br, loses a proton, you have a secondary amine, does it again, lose a proton, you get a tertiary amine, does it again. You don't lose a proton on this last one because there's no proton anymore. And you basically, in the end, get a mixture of primary amine, secondary amine, tertiary amine, and the quaternary ammonium. Why is it an ammonium? Because it's the positively charged amine with 4 things on it. And then we kind of got into these improved methods that avoid all this over-alkylation problem. And there's 2 of them, 2 methods. First one is the Azide method, where you basically, rather than just make the amine directly, you first make an azide, and an azide is a reducible functional group that we can reduce to the amine. So it avoids the whole over-alkylation problem. And then we'll do the second one in a second. So we avoid the over-alkylation problem. The basic idea is, rather than use NH3, we just use NaN3, which is sodium azide. Na, N-, N+, N-. One of the nitrogens kicks off the Br. You're left with an alkyl azide, which is 4 carbons, and then the azide. And then we have this nice way to reduce the azide to an amine, and that creates N2. It'll be, as we'll see in the mechanism, it basically leaves us with that left nitrogen and as an NH2, and the other 2 nitrogens will go away as an N2, N triple bond N. Okay, so that's where we got last time. Now we just have to do the mechanism of this one, and then we'll go on to the improved method number 2, which is a slightly different reaction. Alright, so one thing I want to show is a potential mechanism for how the azide gets reduced to the amine. It's a pretty easy mechanism, but it's not presented in the book, so I'm just kind of making this up. And this is my guess of the mechanism. I think it's a reasonable mechanism. My guess. For how that azide gets reduced to the amine. Alright, so the way I think it happens is you have your azide, and remember you have a plus charge and a minus charge, and we react this with the lithium aluminum hydride, followed by acid water, and you get the amine and N2, nitrogen gas. Okay, so what I think happens is you got your H-, which is lithium aluminum hydride. It's, again, we put it in quotes because it's not exactly free H-. It's actually still attached to the aluminum, but this just helps in our mechanism. So it's a little bit of an approximation. Well, where does hydrogen end up? Which nitrogen does hydrogen end up on? Well, the left one. The left nitrogen gets a hydrogen, at least 1 hydrogen atom, if not 2, from the reducing agent. So we're going to attack the left nitrogen. Okay, so it attacks, and then it pushes onto the positively charged nitrogen. So now we have a hydrogen because we added a hydrogen. And then we have single bond nitrogen, double bond nitrogen, 2 lone pairs, and a negative charge. And we also have a single lone pair on that middle nitrogen now. And I think what happens then is this just swings in, kicks off, and that creates N2, right? So that creates the N triple bond N. And it also creates essentially NH minus, right? NH minus, and then that just grabs a proton from acid, and we're done. So the H3O step in the very end will protonate that NH minus and give you the primary amine. Okay, so that's actually pretty easy. Mechanism, for whatever reason, the book does not present a mechanism, but I thought that was easy enough to explain. And I always would rather present a mechanism than not present a mechanism. Okay, cool. Alright, so that was what I call improved method number 1, which is the Azide method. Now let's do the improved method number 2, which is a different kind of related reaction. Okay. Okay, so now this is going to be a related reaction. We're calling it improved method number 2, and this has a person's name. It's the Gabriel amine synthesis. Gabriel amine synthesis. I don't know the history of Gabriel, but apparently they created this reaction. And remember the improvement we're trying to do is avoid the overalkylation problem that we started this section on. So we just need to we gotta avoid that overalkylation. Okay, so we're just gonna keep this simple and just use bromobutane again, 1-bromobutane. Okay, so we're also gonna do another SN2 reaction. The substrate's a little crazy. It's not that crazy. It's just people always get scared of this when I draw it. So it's potassium, salt, sodium with a negative charge. So it's K plus N minus, and then it's going to be this thing with double bond O, and then a little bond, I guess, there, and a benzene. Okay, so it's essentially K plus N minus, and then double bond O, and then a benzene there. And the name of this thing is called potassium phthalimide. So this alone would be called phthalimide, PHTHALIMIDE. But this with the potassium, it's the potassium salt of it, and it's potassium phthalimide. Potassium PHTHALIMIDE, potassium phthalimide. And DMF, so what is it? What do you think the reaction is going to be? We're using a SN2 solvent, maybe got a good nucleophile, got a good electrophile. All that's going to happen is this is going to attack, and so use a lone pair, attack, kick off the BR, and that's a very clean SN2 reaction, and it's not going to, it can only react once. There's no way it could react a second time. Okay, so what do you get? So these things are attached now, and now you have nitrogen, double bond O, bond, benzene. Don't forget your benzene, double bonds. Okay. So yeah, it's just all it does is SN2, and this is a clean SN2, so you don't have to worry about multiple alkylations. And that's why we call it an improved method. Now the only question is, how do we get to the amine? Because we don't want this whole thing on there. We basically want that NH2, right? We just want to have an NH2 there. Okay, so this is actually pretty easy to do. because this thing is kind of, if you look at it, it's kind of like a amide, but there's two of them, right? There's like an amide and another amide, but overall it has the same reactivity and properties of an amide. And we know that if with amides we can cleave them, right? We can cleave this bond, we can cleave that bond, and then once you cleave them, you're left with the amine, which we want the amine. So all we got to do is cleave this thing. This functional group, which looks like a pair of amides, it's actually called an imide. I-M-I-D-E. So imide refers to like two amides off the same nitrogen. Okay, and that's where you also see imide over here also. Phthalimide. Phthalimide. So now you see that part of the name. Okay, so we can either use H3O plus or OH minus, and usually a little bit of heat, and that will end up cleaving this all off, and you get what we wanted in the first place, which is the primary amine, and of course these both get cleaved to carboxylic acids, so you get this dicarboxylic acid. Oops. Okay, so, and we'll show the mechanism of that. It's a kind of tedious little mechanism. Okay, so this is phthalimide, and you guess what this is? Is a carboxylic acid. This is called phthalic acid, PHTH. Phthalic acid, or you could call it benzene 1,2-dicarboxylic acid, or probably other names also. But that's also the main common name is phthalic acid. Okay, so let's show the mechanism of hydrolysis. Now, just like when we talked about amides and like esters, I kind of emphasized the use of the acid catalyzed one. Because I think the mechanism is more elegant, because you can just protonate like that top oxygen and then just do almost like the reverse Fischer esterification, which is, these are not esters, but it's the same kind of idea as cleaving an ester with acid. So we're going to focus on the mechanism on the acid one. The base one also works, and there's even other ways to do the cleavage reaction, but mechanistically, I think the acid one's kind of maybe the coolest. So we'll show them the acid catalyzed mechanism for the cleavage of the imide to the amine and phthalic acid. Okay, alright, so let's do that. Okay, so what we're going to do is show that mechanism of the hydrolysis step. Which is the second part of the Gabriel amine synthesis. Okay, so we're just going to use, just to be simple, use that same intermediate, the phthalimide. Okay, these steps are reversible, but we're just going to imagine they're irreversible. Okay, we get primary amine and we get phthalic acid. Okay, and probably a little bit of heat. Okay, how are we going to do this? Well, it's just a hydrolysis of these two amides, so probably start by protonating one of the acetyl-Londos. Alright. And yes, probably reversible, but we're going to simplify this and just call them irreversible. Now, because this mechanism is a little bit long, we are going to skip the RSCCs. Now this is an RSCC, and that carbon's electrophilic, but we can just sort of simplify this if we skip the RSCC and just draw a water attack. So water attack directly onto the carbon. You're welcome to draw the RSCCs if you want. It'll take a little bit more time. But water attacks, and now water will be attached. To simplify this a little bit, I'm going to draw the benzene kind of like that. Alright, so the benzene's there. We're just kind of not drawing it every time we do this. Alright. Okay, so now what needs to be kicked off? I mean, we're going to PT. It would not make sense to PT from one oxygen to the other, because what's that going to accomplish? The nitrogen needs to go, right? The nitrogen's being kind of gradually hydrolyzed, right? Eventually the nitrogen's gone, detached. So we're going to PT to the nitrogen. PT to N. Okay, so there's that benzene's kind of attached there. Anything I'm missing? Maybe a charge or something? Are we good? We went from one thing that's positive, so this thing must be positive somewhere. Where's the positive charge? Probably on that nitrogen. Okay. All right, cool. So now we can use one of these oxygens to kick off the nitrogen. So just kick it down and kick off the nitrogen, and that cleaves the bond, but it's still attached through the bottom amide. Okay. So now we have, maybe here's the H. Now we got that, right? Because one oxygen kicked down, nitrogen kicked off. Still all attached through the bottom amide, alright? So we have a top carboxylic acid. This is where we'd usually say, well, minus H plus, right? But what we need to do is cleave the bottom amide now. So now what I do, the way I do it, you're welcome to like deprotonate and then reprotonate this one. I just PT to bottom, because that would allow this one to be hydrolyzed easily, right? So we're going to proton transfer from this top oxygen down to the bottom oxygen. Okay? Okay, so what do we got now? I gotta give myself some space. I'm gonna redraw it a little better to the left. Okay, but we PT'd from that top oxygen down to the bottom oxygen, so now we have a H there and a plus charge here. That's technically an RSCC also, but to simplify this, we're not going to draw the RSCC. We're just going to have water go attack that acetyl bond O. So I'm going to maybe draw off to the left a little bit. Water, got lots of water around. Attack. Kick electrons onto the oxygen. Okay, water attacks, kicks electrons onto the oxygen. Now we have another water attached there on that atom. Okay. Got an OH, OH2 with a plus charge. Got the benzene. Got a carboxylic acid. Alright, that makes sense. So water attached. Now we still have that OH. We also have a water, and I just kind of drew it down underneath there. Okay, what do we always do after nucleophilic attack? Our goal again is to kick off the nitrogen, right? It's got to be kicked off kind of as a leaving group. So now we're going to PT from oxygen to nitrogen, just like we did that earlier, right? We PT'd to nitrogen, now we're going to PT to nitrogen again. PT to nitrogen. Okay. Okay, we PT'd to nitrogen the second time. What's missing? Something's got to be missing. And now it's the charge on nitrogen yet again is missing. Okay, and now we're basically done. All we gotta do is kick off the nitrogen. Use one of those OHs and kick off the nitrogen, and that'll create the amine, right? That'll create the what we want, the primary amine. And then we just have a protonated carboxylic acid, and then we'll just lose that proton and we'll be done. So yeah, the oxygen kicks in, nitrogen goes away. That gives us our product that we care about. And then the byproduct is made with an extra proton on it. Okay, and then we do what? Minus H plus. And we're done. Alright, so that's the kind of long, tedious second step of the Gabriel amine synthesis. All we're really doing is cleaving one amide, then we're cleaving the other amide. Maybe the only thing that's kind of weird here is how we PT'd all the way from one cetyl window all the way to the other cetyl window. That kind of helps. You know, you could draw that as two steps: loss of a proton, gain of a proton, but then it's going to be a kind of a pain, an additional step to an already long mechanism. But yeah, that's the hydrolysis step of the Gabriel amine synthesis. Okay. There's another way to do this cleavage reaction of the Gabriel, another cleavage method. I think the book mentions this, and it's also just kind of a well-known alternate way to cleave the phthalimide. So it's actually pretty easy. I should just mention it. I'm not going to do a detailed mechanism. But if you got your phthalimide, imide, remember I-M-I-D-E, it's an imide, and it's a phthalimide because it's connected to both carbons of a carboxylic acid, or of a benzene there. You can also react this with this stuff. Do you remember what it's called? We saw it in the wet reaction. NH2, NH2, it's called hydrazine. It was in the Wolff-Kishner reaction, remember that? That'll be a fun one to review for the final. So if you have a ketone, remember that you could do NH2, NH2, heat to make a hydrazone. Heat that stuff up with a little bit of, sorry, just heat it basically, and then the ketone goes away. So it's a way to deoxygenate a ketone or aldehyde. So it's called the Wolff-Kishner reaction. Okay, but we're not going to use it for a Wolff-Kishner application here. What we're going to do is just use it as a nucleophile. So hydrazine, which is NH2NH2, is a super duper nucleophile. It loves to react as a nucleophile. The basic thing that happens is as a good nucleophile, it just attacks. You don't need activation of the double bond O or anything. So it attacks, and then kind of like the other side attacks the bottom, and it cleaves off the amine, and you get basically, after a silly little mechanism, you kind of get this sort of thing with another 6-member ring, I guess. So you got a benzene, and then like this NH thing is kind of attached to the two double bond O's. I didn't draw it too well, but you can imagine this is just a nice hexagon 6-member ring. Okay. All right. So that is another way to do the cleavage. I think it's milder, so you don't have to apply as much heat or time. I think this is, because it's such a good nucleophile, this is a pretty favorable reaction. Side note, that byproduct, the byproduct of this hydrazine-mediated cleavage of the Gabriel, is related, kind of, or similar in structure to something called luminol, which is kind of an interesting molecule. Luminol, which is a it's like glow sticks, right? So what's luminol? It glows in the presence of certain chemicals. So it's the same thing, except it's got an amine there. Here, I'll draw it a little nicer here. There we go, that's a little better. So this is the same thing, drawn nicer, and we have the NH2 there. This stuff's called luminol, and it's found in like glow sticks, which you've probably seen or played around with before. So this stuff, interestingly, in the presence of hydroxide, or oxygen, or bleach, or actually blood, cleaves to the phthalic acid, the aminophthalic acid. Benzene, NH2, and it produces light. So it actually produces a photon of light, and that's how it could be used as glow sticks. And why is this interesting that blood does this, and like the iron in blood, is because this is actually used in like crime scene investigations and forensic science. So in a forensics investigation, they can kind of spray this around in a room, and then wear glasses where you can actually see light being emitted. It's like a chemical luminescence type thing. So anyway, that's kind of a little side note thing. And this is randomly structurally related to this byproduct of the Gabriel, which I drew kind of poorly. It's again just a 6-member ring, like a hexagon, and then a benzene. Yeah. Okay, so that's what luminol is, and that's kind of what it does, and what an application of it is in like forensics, and also like just as kind of a fun kid's toy of little glow sticks that you've probably seen around. Okay, that's luminol. Okay, so I said there was two methods, two alternate methods to the synthesis of primary amines. We said the Azide method and the Gabriel method. There is actually a third method, but it's and you actually know this one already, but it's just a little bit different. Well, we're going to review it real quick. I'm going to call it method number 3. All right, so there's not just two, there's a third one, and this is using nitriles. Okay, so, but the thing about using a nitrile to accomplish this, you know how we kind of like started the bromide and we made a phthalimide type thing, and then we cleaved off the phthalimide. The thing about a nitrile is that it adds an extra carbon. So it's cool because it does what we want to do, but it does add an extra carbon. So you have to be aware of that when you use this reaction. Okay, so the method for method number 3 is, let's just start with 4 carbons and a Br, and then let's do another SN2 reaction. How do we make a nitrile? Nice linear nitrile, don't draw it bent. How do you make a nitrile? 4 carbons in, 5 carbons out. 1, 2, 3, 4, 5. So maybe NaCN, and like DMF. So it's a simple SN2 reaction, organic 1 style. Kick off the Br, now you got a nitrile. Okay. And so we add an extra carbon. Then the question is, well, how do you convert a nitrile to a primary amine? 1, 2, 3, 4, 5 carbons, NH2. You know how to do that. That was something you learned chapters ago. It looks like we're adding what appears to be 2 hydrogens, so maybe something that adds hydrogens. What's the reagent? It's actually, I think it's the end of last chapter, chapter 20, I think. We did this also. You can do a double reduction of the nitrile to the amine, and that's just using lithium aluminum hydride and acid. Okay, so that does what we want to do of converting a bromide to a primary amine, but it does add an extra carbon. And what's the mechanism of that? I'm not going to review that mechanism because you've seen it multiple times now. But it's, in a nutshell, it just hydride attacks. Maybe put some quotes around there. So what happens is it attacks once and you get an N minus, and then it attacks again and you get an N2 minus. So it's like it makes N minus, then makes N2 minus, and then the acid protonates those N minuses, and you get 2 protons and you get a primary amine. Okay, so that is also one that you've seen. Okay, so let's summarize these method 1, 2, and 3 real quick. So if I have a alkyl halide like benzyl bromide, which is phenyl CH2 bromide, there's kind of like three ways we can do the alkylation. 2 of them that just directly give you the primary amine, and a third way that gives you primary amine plus an extra carbon. Okay, so method 1, as we described it, was the Azide method. So NaN3, lithium aluminum hydride, AlH4 H3O plus. Okay. Let's see. The second one, I'm gonna draw it kind of small. It's that phthalimid thing, right? So you have to be. Let's see. Let's draw this underneath. Give myself more space. Okay. Okay. So the second one was the potassium N minus double bond O benzene thing, and then usually like H3O plus or something. Okay, so that was like here's like an azide attacks, then you reduce the azide. Here's this phthalimid thing attacks, then you do the hydrolysis, and you get primary amine. Okay, so these are one result, and this is the other result, and the third one is basically NaCN. Whoops, like NaCN. Make a nitrile, lithium aluminum hydride. You need like a acid workup with H3O plus. Okay, so that was a little summary of those different methods that we just learned. Okay, so that's the end of number 6, which was talking about like alkylation methods to make primary amines. Now we're into number 7, which is a very general other way to make amines. So this is a way to make synthesis of primary, secondary, and tertiary amines by a method called reductive amination. Reductive, which probably means what? What does reductive mean? Probably the use of a reducing agent, like a hydride or something like that. So reductive amination is this method that it's just a kind of cool way to build amines. So this is a very general reaction. I'll put a couple stars, and you're going to definitely expect to see this on the quizzes and stuff. What is it? So let's show an overview of kind of what is the main process of reductive amination. So the overview and the scheme in general is that we're going to make an imine. Remember imines? Probably forgot what imines are. We can make an imine. I'll show what an imine is in a second. Or iminium. Imine or iminium, which is just a positively charged imine. And then we're going to reduce it to an amine. Okay, so make an imine or iminium, then we're going to reduce it. How do you reduce things? It's basically going to be a special H- reagent. H-, it's not the same. Usually we use a specific H- reagent that's a little different than the ones you're used to, just to make it exciting. The one that we're going to highlight, and which the book also highlights, is NaCN BH3. Okay, so this is a different hydride reagent. It's it's kind of like almost looks like NaBH4, which you should remember from Organic 1. But there's some reasons why this is actually ideal, and it works really well for this reductive amination concept. Okay, so we're going to see a lot of NaCN BH3, which is called sodium Cyanoborohydride. Okay, so what's an example of this whole thing? Here's a simple example. I get an amine. Let's react it with a ketone. What happens when you react amines and ketones? I don't know. Remember this from chapter 17, I think it was? Is that you make amines, right? the N attaches to where the double bond O is. It's a fun, cool little mechanism. You basically end up with nitrogen double bound to the carbon, and the oxygen goes away as water, right? You lose H2O, right? Okay, so what that gives you is the imine, right? First you get the imine, and then the imine is going to be reduced to give the amine. And the amine is simply just, assume you have an H there and an H there, so it's going to be the amine. So we added an H onto the nitrogen, and of course there's an H there. We don't have to show that one. But this is reductive amination in a nutshell. Okay, amine plus ketone or aldehyde makes an imine. We'll see iminium ones also in a bit. And then this gets reduced. So essentially what happens is H minus is this stuff's NaCNBH3, and so this essentially just attacks the imine as kind of a reducible functional group. Right? H minus attacks the carbon, kicks the electrons onto the nitrogen, and then we get some sort of protonation from methanol or solvent or whatever, so the NH gets its proton. So we're skipping that protonation step. But this is the reduction part. For step 1, make an imine or iminium. Step 2, reduce, and then you get your amine. And the reagent again is NaCNBH3, and it's usually at a slightly low pH. So the reagent, I'll draw it over the arrow. NaCNBH3 methanol is a solvent normally, and we'll say pH 2 to 3. Another way to say pH 2 to 3 is catalytic H+, right? 2 to 3 is acidic, it's slightly acidic. So you usually would just add a little bit of acid to your methanol, and yeah. But that is, pH 2 to 3 basically means there's some H+ around, catalytic acid. And your final product is the amine. That is the overview of reductive amination. So now let's show some examples of it. Oh, the other thing, and if you're following along in the book, which is a good idea, the book also shows an alternate reducing agent, basically. So if you're reading along in the book, and just so you don't get confused, the book sometimes shows H2 nickel as the thing that does the reduction. So of course H2 adds an H and another H. So it's like a reduction of the imine by addition of H2 to the nitrogen and the carbon. So anyway, that's another way to do it. For this course I usually just emphasize NaCNBH3, which again, what's it called? Sodium cyanoborohydride. Okay. Okay, so let's show some examples of this. Now, one example, we'll call it B, is making a primary amine. Making a primary amine with red am, which is another way of saying reductive amination. Reductive amination. So primary amine, an example of this would be like, you got a ketone and you want to make a primary amine. Ketone to primary amine. What's the amine we're going to use? Is it amine containing carbon, or, well, let's make this NH2, sorry. Is there any carbons on this amine? Because remember, it's like going to be a ketone and then some kind of amine type thing, and makes an imine, and then we reduce it. But we're going from 6 carbons to 6 carbons, so all we use is just NH3, ammonia. Ammonia, and what are the reagents? NaCNBH3, pH 2 to 3, or you could say H plus cat is another way to say that. And what's the intermediate? Imine, a simple imine, a boring imine with just an NH on there. That's an example of a very simple imine, right? Yeah, and remember when we did imine formation in chapter whatever 17, I think it was, how we always had acid catalyst? Because what was the mechanism of this, right? Oxygen grabs the proton, and then the ammonia attacks, right? Proton transfer to the oxygen. That's like right when you were learning about proton transfers and stuff. So it's like you protonate the oxygen, NH3 attacks, and you proton transfer to the oxygen, and you're able to kick off the oxygen as a leaving group using nitrogen, and then you lose an extra proton and you get the imine. And then the reduction step is really easy, like we just showed. If you just assume H minus, I mean it's really trivial. Hydrogen attacks, kicks electrons up, and then you get N minus, and the N minus gets a proton from methanol. Usually, you get some methanol in there too. Okay, so you have a proton source that can give you that extra proton. So it's like ammonia, NaCNBH3, methanol. You need a solvent, and then slightly low pH, and then out comes the primary amine. Okay, next one. Making a secondary amine. With reductive amination. So let's make a secondary amine now, and let's use a different ketone this time. Okay, we have a ketone. To make a secondary amine, well, think about, back to this problem up here. Here we're making a primary amine, and we used like an unsubstituted nitrogen, like a ammonia. When we make a secondary amine, like that, okay, what kind of amine are we going to use now? I mean, of course, the structure of the amine will just be that, right? It's going to be, is that a primary amine, secondary amine, or a tertiary amine? Looks like a primary amine, right? It's ethylamine, right? Yeah, so a primary amine in will make a secondary amine out. That's what I'm trying to show. Okay? So the amine we're going to use now is primary amine, and the product will be a secondary amine, because of course there's 2 carbons on the nitrogen. Okay? What are the other reagents we need for reductive amination? The same stuff as above. NaCNBH3, methanol, low pH, or you could say H plus cat. NaCNBH3, methanol as a solvent. This time I'll just say H plus cat. Alternatively, you could just say pH 2 to 3. Okay. What is the imine going to look like? Or like here, how we made an imine. You always go through an imine type thing in the reductive amination. So of course, the nitrogen attacks the carbon. You know, first you protonate the oxygen, and then the nitrogen attacks. Basically replaces off the double bond O. So the imine structure is going to be that, but with the nitrogen. This is the imine. And then you H minus to reduce the imine. H minus excited, which basically means first we reduce it and then we protonate the nitrogen with methanol. I could maybe draw that. This is a second arrow. Methanol. So H minus puts a hydrogen on the carbon, and the methanol provides a proton to the nitrogen, right? Because you get an N minus grabs the proton from methanol. Cool. That's making a secondary amine with reductive amination. First we made a primary amine, now we made a secondary amine. What's the next one we have to do? Okay, so we're going to make a tertiary amine, right? With reductive amination. Okay, so to make a secondary amine, we used a primary amine, right? Primary amine plus ketone or aldehyde. And that, when we made the amine, reduced it, you got a secondary amine. So now the question is, if we're going to make a tertiary amine, and I'm going to go back, we'll use cyclopentanone this time, just to switch it up. It can be ketone or aldehyde. What kind of amine am I going to react with to make a tertiary amine? I'll make methyl ethyl. That's a nice tertiary amine, right? Okay, so up here we used a secondary amine and the product was a tertiary amine. No, I'm sorry. Primary amine and the product was a secondary amine. So here, what kind of amine is it in and what kind of amine is it out? It's going to be a secondary amine in and a tertiary amine out. Okay, that makes sense? And what's the amine going to look like? Well, get your hand out and it's going to be that, right? It's going to be, all we're going to do is react it with methyl ethylamine. That's going to be the amine we're going to use. We're going to have a secondary amine in and a tertiary amine out. So there's a secondary amine in, tertiary amine out. Same remaining steps, NaCN-BH3, methanol, H plus cat, or low pH. But the thing is that when the secondary amine reacts with a ketone, you might remember that from the chapter 17 that it actually, secondary amines would usually make something called an enamine, but it first makes something called an iminium, and we're going to make the iminium. I'll draw the iminium, and I'll remind you what the enamine is too. What the iminium is. The iminium is going to look like the imine, right? It's basically going to be carbon double bond to nitrogen. Okay, so these two are going to react, and you're going to get something that looks like. There's our 5-member ring. We're going to get an iminium intermediate. It's not an imine, it's an iminium. Where's the charge? This iminium is a charged thing. Where's the charge? It's on the nitrogen, right? It's plus charge on nitrogen. Okay. Iminium is, the definition of iminium is it's a charged imine. So that was a uncharged thing. The imine's uncharged. Iminium's a charged thing. Okay. Okay, so you get this, and then now it's just a reduction to make the tertiary amine. H minus, circle the lone pair, attacks the carbon, electrons go up. Now there's actually no protonation step. It's not like you need to protonate the nitrogen because there's no proton that needs to be incorporated. It simply reduces. This is the NaCN-BH3 is hydride. Let's draw that nicer. H. Okay. That's still drawn pretty poorly. Let's make it a nice H. Okay, there we go. H minus attacks. But you don't actually have to protonate the nitrogen as a second step. It's just all you do is the reduction. Okay. Just to review what I was saying a second ago, like, you know, back in chapter 17 when we did ketones and secondary amines like this. This is back review from chapter 17. What we learned was that, I'll draw the same thing. Nitrogen, secondary amine, was that we get an enamine. Remember enamines? Just want to review that word. Enamine is an alkene meets an amine, right? And when you learned about this, we did show how an iminium formed in the process of this. Iminium. So if you look back in chapter 17, this is what you'll see. We also showed, oh yeah, there's acid catalysis. So it's all, you know, it's straightforward. Oxygen grabs a proton, you make an RSCC, nitrogen attacks the RSCC, proton transfer onto the oxygen, and then essentially nitrogen kicks off the oxygen and you get the iminium. How do you get the enamine then? It was the base, which is the base is probably just the amine, because amines are basic. Rips off the proton and you get the enamine. So what's different in this chapter? Because we're doing the same thing. The difference is when you form the iminium, we immediately reduce it. So it's not like the iminium's hanging around and forming the enamine. You make the iminium, it's instantly reduced with the H- that's present. It's a reducing agent. Okay, and your net result is we go with a secondary amine in and we make a tertiary amine out. So that's a good introduction to reductive amination. Okay, another little tidbit about reductive amination is that, and the book mentions this also, we can do it in a couple different manners. We can do kind of like what I'm going to call it a one-pot procedure versus a two-step procedure. So we do see both of these methods in the kind of like in chemistry. Okay, so by one pot versus two-step, it's kind of like do everything in a single step versus doing it as a two-step thing. Let's just show an example of this so it's clear. Here's an aldehyde. Okay, so of course we can do reductive amination with ketones. We can do it with aldehydes. Let's use an amine, H2N, with a cyclopropyl. It's kind of exciting. Different molecule. Let's draw that a little better. Oh, there we go. Alright. And so we can either make the amine and then reduce it, like as a procedural step, or we can do it all at the same time. It seems kind of trivial, but in the lab, there's reasons you want to do it one way or the other. Okay, so if we want to make an amine as a separate step, it's like aldehyde, amine, and then the catalytic acid. And then what's the amine going to look like? Well, the nitrogen is going to be connected to the carbon, right? And then you have a CH2 and a cyclopropane. Okay, so there we go. And then we have a CH2 and a cyclopropane. Okay, there you go, there's an imine. So we can do this as a kind of sequential process where we like, let's make an imine, because we know how to make imines. It was done in chapter 17. And then we can actually add a reducing agent. Now we can actually use other reducing agents here too, including like NaBH4, which we have seen before, right? That we used that for ketones and aldehydes, NaBH4. We also can do this H2 nickel thing, and then that just reduces it, because the net goal is to reduce the amine to an amine, and your final product is that. Okay, now we have two H's, and you got the amine. All right, cool. So this is kind of like a two-step process where we purposefully make the amine, and then we throw in a reducing agent, either NaBH4 or like H2 nickel, and then you get the final product out. Okay, how does that differentiate from the one-pot procedure, which is kind of like what we were highlighting all around, is that we could just do this all in one step, just by throwing everything in there at the same time, which is kind of the beauty of the NaCNBH4, BH3, sorry, method. NaCNBH3, pH 2 to 3 methanol, where we just essentially add everything into one pot, and it makes the amine and it immediately reduces it. So you can see, like, procedurally, this is kind of cool. We just kind of mix everything up and out comes the product. That's why this is kind of a cool, alternate reaction. And this is what we were kind of highlighting the whole time in this section. But I'm just pointing out that you can also just make the amine and then sometimes even purify and isolate the amine and then do a reduction, some kind of reduction step. Okay, two-step method or one-step method, get to the same product. Okay, so that all said, generally people like the one-pot method. One-pot method. And by one pot, I mean the bottom one, which is add everything. And in this class, in this class, in chem335, we're probably just going to emphasize this bottom method. One pot method. Because it's an introductory course, and we want to keep things kind of simple. So yeah, NaCNBH3 methanol pH 2 to 3 does everything in one step. Okay, so let's kind of apply this method, the reductive amination method, in synthesis. Synthesis via reductive amination. So by synthesis we usually mean going backwards. So we look at a product and we're like, how are we going to make this product? I'm going to show an example. We'll show one good example, and then we can actually have you try one that you can practice this approach. Let's consider a molecule like fluoxetine, which is Prozac. So we have a couple, we have an amine in there, and we have a little bit of other stuff. There's a benzene with a CF3. Okay, so that's fluoxetine, which is Prozac. And we're going to synthesize the amine through reductive amination. And there's kind of two ways you can do this, because remember the the I mean, reductive amination is like you would make this amine from an imine or iminium, right? So I can envision, well, the imine's either going to be there or the imine's going to be right there. So we actually have two different approaches, A and B. Alright, so we have A and we have B. Alright, cool. So we're going backwards. This is a retrosynthesis. So I have approach A, I have approach B. In one case the imine's one direction, and in the other case the imine's the other direction, and then we can build the imine through, you know, how we build imines, from amines and ketones or aldehydes. Okay, so I can envision the amine be here. I'm going to abbreviate the trifluoromethylbenzene as AR. So pH is phenyl with nothing on it. OAR in this situation is the benzene with the CF3 on there, just to make this a little bit easier. And of course, this is the imine, right? And you can imagine, well, we have an H there and you have an H there. That is an amine. For B, I'm going to have it kind of going downward because I'm going to run out of space. Okay. Alright, so, and then how do you build this imine? And we're going backwards, so how do we build the imine? Well, what's the bond that's being formed in an imine formation? It's there. Alright, so we're going to have a right side piece, which is the amine, right? We're going to have a left side piece, which is ketone or aldehyde, right, with how many carbons? One carbon. So it's going to be a very simple one carbon aldehyde, also called something aldehyde. What's the one carbon aldehyde, you know? It's formaldehyde, right? So this imine can be produced from formaldehyde, the simplest aldehyde, and ch21 OAR pH from this primary amine. Of course, this primary amine could be made also, so you could actually keep going backwards and make this, you know, we just learned about primary amine synthesis by a couple of different methods, Gabriel, Azide, and even the Nitrile method. Lots of ways you can make primary amines, or you can do a primary amine through reductive amination. But yeah, but essentially if we took these two pieces and throw in NaCNBH3, methanol, and pH 2 to 3, out would come Prozac, right? Fluoxetine. Okay, what's method B then? Here, for method A, we were saying, oh, the imine's going to be there, but for method B, oh, the imine's going to be there now. So, okay, so now we just draw a different imine. See how we did it? Just assume the imine is going to be right there. Okay, and how do we make an imine, and what are the pieces to make an imine? Where's the squiggly line to make an imine as we go backwards? You know, if we want to make that, we would make it from an amine of how many carbons is that? It's a one carbon amine, methyl amine. Right, there's a CH3 right there. Amine of one carbon, and in this case probably an aldehyde with this whole thing, right? Aldehyde. Okay, so we can make this and draw the little squiggly line maybe from methylamine, one carbon amine, and then the aldehyde. And there you go. Of course the reagents are the same. NaCNBH3, methanol, pH 2 to 3. Okay. So that just showed kind of two different approaches to make a molecule like the antidepressant fluoxetine or Prozac through reductive amination. Here's just one for you to try. You can try it yourself and send it to me if you want. Feedback. You try this one. It's just a random amine I just kind of came up with of like no pharmacological significance. But you can envision that this amine could be made by an A approach and a B approach, where you're basically going to break it down into, the A approach, you'll break it down into 2 molecules, and the B approach, you'll break it down into 2 molecules. The trick will be, maybe you should draw an imine there, or an imine there, and then you can, once you have the imine, you can break it down into probably aldehyde and an amine, or another aldehyde and an amine. All right. Here's one more. You try. What if we change this around a bit and now it's a tertiary amine. So now there's going to be 3 different approaches. A, B, and C. And remember when we made tertiary amines, we didn't make them from imines, we made them from iminiums. So you can imagine an iminium there, maybe for A. You can imagine maybe an iminium there for B. Or you can maybe imagine an iminium there for C. Once you have those, you can make iminiums from secondary amines and probably aldehydes, I think, in these cases. So you could try that also as just another kind of synthesis practice thing for reductive amination. Okay, basically at the end of the lecture, I'll just tell you what number 8 is going to be. I think most of the hard stuff's done. We have just a little bit more in this chapter. We actually made a lot of progress in this chapter. Number 8 is synthesis of amines from amides, which you already know about. We learned about that already, right? You can take amides and reduce them, right? And there's basically going to be 2 methods to do this, and we'll review them next time. You already know them, so nothing's really new here. One's called direct reduction, where you basically make an amide and reduce it. How do you reduce an amide? Lithium aluminum hydride, right? We learned this before. And the other thing was that Hoffman thing. Hoffman Rearrangement, which we already know about also. That was that weird thing where you had a primary amide and it lost CO2 and it degraded a little bit with loss of CO2. And those are both methods to make amines from amides. Okay, and you know these both, so we'll spend a little bit of time reviewing them next time. Okay, that's it.